Hey everyone, welcome to the fourth week of General Chemistry. And for this week, we are going to talk about molecular geometry and polarity of molecules. So what is molecular geometry? Molecular geometry pertains to the three-dimensional arrangement of atoms in a molecule. As seen on the animated pictures on this slide, these are examples of molecular geometry. And why do we need to know about the geometry of molecules? Geometry affects the physical and chemical properties of molecules and their reactivity towards other molecules. And molecular geometry also helps us to determine the polarity of the molecules. So when we say polarity of molecules, we have here a determiner. Polar molecules exhibit dipole moments and nonpolar molecules have no dipole moments. So when we say dipole moment, the charges on the ends of the molecule must be equal in magnitude but opposite in sign. So for example, this is the structure of the molecule. One end must be positive, the other end must be negative. That's why it's called dipole. And nonpolar molecules do not exhibit this dipole moment. So considering now the bent shape of water in here, in the first picture, and take note that the dipole moment always points from partial positive to partial negative. Okay, so in here, oxygen is charged partially negative because oxygen is more electronegative than hydrogen. So the two dipoles from each side, from the hydrogen, are directed towards the central atom, which is the oxygen. Okay. And it results to an upward net dipole moment, making the water molecule polar. So both the movement of the electrons in here are upward towards the oxygen. So if that is the case, therefore, the direction of the dipole moment is like this on the arrow on this side. It's upward. So one end is negative, the other end is positive. Therefore, water is a polar molecule. While on the carbon dioxide in here, as you can observe, since oxygen is more electronegative than the carbon, it pulls the shared pairs of electrons closer to itself. So the electrons in here, the movement will be towards the oxygen since oxygen is more electronegative. Hence, it has a partial negative charge for oxygen and partial positive charge for carbon. And since the arrows are in opposite directions, you may imagine it like a tug of war. They are pulling each other on opposite directions. They will cancel out. Okay? And if the dipole moment cancels out, then this molecule, therefore, is a nonpolar molecule. Now, let's proceed to determining polarity of molecules from their molecular geometry and Lewis structure. So, let us now apply our knowledge on drawing Lewis structure and the different types of molecular geometry to determine the polarity of molecules. So, we have actually 11 types of molecular geometry. Let's begin with linear geometry. For linear geometry, we are going to take beryllium chloride as an example. The general structure for a linear geometry is this. So we have here the central atom, then we have two attached atoms. Okay, so that is linear. Now going back to BeCl2, we are now going to draw the Lewis structure of this one. For Be, it belongs to group 2. So it has 2 electrons, 2 valence electrons, and Cl belongs to group 7 times 2 because it has 2 atoms of chlorine. So this will be 2, this will be 14. The total valence electrons is 16. So 16 must be shown on our structure. So if we are going to draw it, since B beryllium is only 1, then therefore that is the central atom. So we have BeCl, another Cl. And then take note, since beryllium belongs to group 2, the number of bonds that it could make is also 2. Okay, this rule was already discussed in the previous week. And then for chlorine, since it belongs to group 7, then it could make 7 bonds. So we have, just to complete the octet rule, we have 2, 4, 6, and 8 for this line. And then for the other chlorine, we have 2, 3, 4, 5, 6, 7, and 8. Okay, so here is now the final structure, Lewis structure for beryllium chloride. Now, how are we going to determine if this structure or this molecule is polar or non-polar? So here's the rule. If the central atom doesn't have lone pairs, it has no lone pairs, then therefore the structure is non-polar. Okay? And if the structure is symmetrical, meaning say if you are going to divide this into half and they have the same structure on both sides, then it's also non-polar. If, for example, there are lone pairs in the central atom and it's not symmetrical, then the molecule is polar. So as easy as that. Another structure is bent. Our example here will be water. The general structure for bent structures or bent geometry is this. So we have here the central atom, still 2 attached atoms with 1 lone pair in the central atom. Or it could also be the central atom plus the 2 attached atoms with 4 dots or 2 lone pairs at the central atom. So let's check water as an example. Hydrogen belongs to group 1 times 2 because it has 2 atoms. Oxygen belongs to group 6. So this is 2, this is 6. Total valence electrons is 8. So for hydrogen, for water I should say, oxygen here is only 1. So that will be our central atom. So we have O, and then H, and then H. I'm sorry for the general structure, you make this bent. Okay, let me correct this one. This makes it different from the linear structure that we have. So I'm so sorry, this should be a little bent. Okay. So for oxygen, we have here O bonded with 2 hydrogen atoms. And then take note, hydrogen can only hold a maximum of 2 electrons. Therefore, hydrogen will not necessarily fulfill the rule of 8. But oxygen, it must obey the octet rule since it's the central atom. So for oxygen, it has 2, 4, 5, 6, 7, and 8. Okay, as I have mentioned a while back, if the central atom has lone pairs, then the structure is polar. Okay, and take note, all bent structures are polar. The third molecular geometry is the trigonal planar. And we are going to take boron trihydride or borane as an example. The general structure for trigonal planar is we have here a central atom, and this time we have 3 attached atoms. So if you are going to draw trigonal planar later on, you just have to follow this general structure. So we have 3 attached atoms. So boron belongs to group 3. Hydrogen belongs to group 1 times 3. So we have here 3 plus 3. All in all, we have 6 electrons. So if we are going to draw the Lewis structure for BH3, it would simply be B, H, H, and then H. Take note that boron belongs to group 3. That's why it could only make 3 number of bonds. So since it has 3 already, then it doesn't necessarily need to meet the octet rule. So this is now the final structure for boron trihydride. And since the central atom doesn't have any lone pair, and the structure is symmetrical, therefore this structure is non-polar. The molecule is non-polar. The fourth structure or geometry is trigonal pyramidal. So we'll take ammonia as an example. For trigonal pyramidal, the general structure is we have a central atom with 3 attached atoms, and it has a lone pair at the central atom. So this is the general structure of trigonal pyramidal. So nitrogen belongs to group 5 and hydrogen belongs to group 1 times 3 of it. So we have 5, 3, the total electrons is 8. So if we are going now to draw the Lewis structure for NH3, N is the central atom, then we have H, H, and another H. So if you are going to count now, we have 2, 4, 6. We need 2 more. So the dots will be put on nitrogen, so that it will make 2, 4, 6, and 8. And since hydrogen can only hold a maximum of 2, it doesn't need to meet the octet rule. So this is now the final structure for NH3. And since it has a lone pair at the central atom, then this structure is polar. Next is the T-shaped. So we are going to take iodine trifluoride as an example. The general structure for T-shaped molecules is we have a central atom still with 3 attached atoms. But what's the difference between T-shaped and trigonal pyramidal is that T-shaped has 4 dots, or it has 2 lone pairs. For trigonal pyramidal a while back, it has only 1 pair. But for T-shaped, it has 2 lone pairs. Okay, for iodine, it belongs to group 7, and fluorine also belongs to group 7 times 3. So we have here 7, we have 21. The total is 28 electrons. So since iodine here is the atom with only 1, then it is the central atom. So we have I, F, F, and then another F. So let's check if they obeyed the octet rule for each. So for this first fluorine, it only has 2. So we are going to write 6 dots more to make it 8. And so with the fluorine here, and also this one. Now if you are going to count the whole structure now, we have 8, 16, 24. So it needs 4 more. And we are going to write it on iodine. So we are going to write 4 dots. 1, 2, 3, and 4 to make the structure 28. Okay. So this is now the final structure for iodine trifluoride. And since it has lone pairs at the central atom, this structure is polar. The sixth geometry is the tetrahedral. And the general structure for tetrahedral geometry is this. So we have a central atom with 4 attached atoms. So you are going to follow this drawing if the geometry is tetrahedral. So let's take SiF4. So silicon belongs to group 4 and fluorine belongs to group 7 times 4. So we have 4 and then 28 All in all, it has 32 electrons. So silicon is our central atom in here. So we have Si with 4 fluorine. F, F, and then letter F. And then take note that silicon now here could make 4 number of bonds, and it has 8 electrons already. So 2, 4, 6, 8. We also need to complete 8 electrons for each fluorine atom. Okay, so all in all, if you are going to count the electrons for the whole structure, it has 32 electrons. Now, since the central atom doesn't have any lone pair, then this structure or this molecule is non-polar. So, silicon tetrafluoride is a non-polar molecule. The seventh one is the seesaw. For seesaw, the general structure is, we have here the central atom with, again, 4 attached atoms. But this time, it has a lone pair at the central atom. So, sulfur belongs to group 6. Fluorine belongs to group 7 times 4. We have 6. We have 28. The total is 34 electrons. So if we are going now to draw the structure for sulfur tetrafluoride, since sulfur is only one, it will be the central atom, and then with 4 attached fluorine. Okay, so sulfur could make 6 bonds, while fluorine could make 7 bonds because it belongs to group 7. So let's now complete each with 8 electrons. So we have 2, 4, 6, 8. 8 also for this fluorine, and 8 for this fluorine. So if we are now going to count, we have here fluorine. Each fluorine has 8 electrons already, and sulfur has also 8 electrons already. But since sulfur belongs to group 3, and if you can still remember that if the central atom belongs to group 3 and beyond, group 3, 4, 5, 6, and 7, it could hold more than 8 electrons, right? So sulfur has 2 dots in here because as we have said, that sulfur belongs to period 3, and period 3 and beyond atoms could hold more than 8 electrons. So it's still correct that sulfur in here has 2, 4, 6, 8, and 10 electrons. So this structure is still correct. And all in all, if you are going to check, we already put the 34 electrons. And since the central atom has a lone pair, this structure therefore is polar. Therefore, sulfur tetrafluoride is a polar molecule. Now, the eighth geometry is the square planar. For square planar, the general structure is we have here the central atom with still 4 attached atoms, but it has 2 lone pairs. Okay, so we have 4 dots around the central atom. For xenon, it belongs to group 8, and fluorine belongs to group 7 times 4. So this is 8, this is 28. All in all, we have 36 electrons. So if we are now going to draw the structure, we have xenon as the central atom because it's the atom with only 1. And then we have 4 fluorine atoms. Okay, so we need to fulfill each fluorine atom with 8 electrons. And then let's check afterwards if we already put 36 electrons all in all. Okay, so we have here 8, 16, 24, 32. So we need 4 electrons more. The 4 remaining electrons will be drawn on the central atom. So we have 1, 2, 3, 4. So you kindly check if there are 36 electrons in this structure already. So since we already have 36 electrons, then the structure is correct. Now take note for this square planar, please remember that this is an exception to the rule that if the central atom has lone pairs, then that is a polar molecule. For square planar, my dear students, kindly take note, the square planars are non-polar molecules even though they have lone pairs at the center. An exception here is that if there is an even number of lone pairs, we must check the structure properly. And since the square planar also is symmetrical in structure, if you are going to divide this into two, both sides are the same or they are symmetrical. This makes square planar and non-polar geometry. So again, may I repeat that square planar is an exception to the rule that I've mentioned a while back that if the central atom has lone pairs, then automatic that is polar. For square planar's case, it's not applicable. Okay. The ninth geometry is the trigonal bipyramidal. The general structure is we have here a central atom with 5 attached atoms this time. So here is how to draw properly the trigonal bipyramidal. Okay. So for phosphorus, it belongs to group 5 and chlorine belongs to group 7 times 5. So we have 5, 35. The total is 40 electrons. So we just have to simply distribute now the electrons. We have P and then Cl, chlorine, 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 and chlorine. So automatically, if that structure or if that molecule has 5 attached atoms and it has exactly 40 electrons, then the geometry is trigonal bipyramidal. And then you complete the chlorine with 8 electrons. Okay, so phosphorus in here carries 10 electrons because phosphorus belongs to period 4. So again, it could hold more than 8 electrons. It's an exception to the octet rule. And since the central atom in here doesn't have any lone pairs, then this structure is non-polar. Next is a square pyramidal. For square pyramidal, the general structure is that it has a central atom with still 5 attached atoms. But what makes it different to trigonal bipyramidal is that it has a lone pair at the central atom. Okay, so taking now the example, we have iodine which belongs to group 7. Fluorine belongs to group 7 times 5. This is 7. This is 35. So all in all, it has 42 electrons. So if we are now going to draw the Lewis structure, iodine will be the central atom with 5 fluorine. And each fluorine will have to make or meet 8 electrons each. And then if you are now going to count, here we have 8, 16, 24, 32, 40. So we still need 2 dots. So that will be at the central atom to make the whole. Okay. So since it has already 42 electrons and the central atom has a lone pair, therefore this molecule is polar. So iodine pentafluoride is a polar molecule. The last structure now is the octahedral. Octahedral has a general structure of this. So we have here the central atom with 6 attached atoms. So it's like an asterisk. Okay. And then for sulfur, it belongs to group 6 and fluorine belongs to group 7 times 6. So we have here 6. We have here 42. All in all, it's 48 electrons. So sulfur is the central atom. We have F. Okay, since sulfur belongs to period 3, again, it could hold more than 8 electrons. So we now complete the octet rule for each fluorine. Okay, so check now if there are 48 electrons all in all. So we have 8, 16, 24, 32, 40, 48. Okay, so since the central atom doesn't have a lone pair, then this structure is non-polar. Therefore, sulfur hexafluoride is non-polar. So just a recap on what we have discussed. Therefore, you can say that that structure or that molecule is polar if the Lewis structure has lone pairs in the central atom or the attached atoms are different. Okay, and that molecule is non-polar if it doesn't have any lone pair at the central atom except for square planar. So I hope you see the differences of the different molecular geometries. If you have any questions, feel free to ask it in our LMS discussion board or you may ask it in our group chat. So once again, thank you for watching, and I want to end this lecture with this quotation: bonding through dependence never works, whereas bonding through freedom always does. Good day, everyone.